And on to the highest region, 20 to 30 pounds per minute. We used a KC value of 8.7% per pound per minute, which was the maximum reasonable KC value, using the same parameters that we used in the model. We found this to be underdamped with a decay ratio of just under 1. It does not settle as far as our data tells, and it is oscillatory. And the minimum reasonable KC value of 0.5% per pound per minute. So we found this to be overdamped with a 1/500 decay ratio. It is monotonic, and the settling time is around 10 seconds. And this is just inconsistencies with the system. So we could pretty much call that settled. And today, in conclusion, we went over the proportional only model and experimental results. We found that the differences between the experimental results and the modeling results was just inconsistencies with the system and system error. Let's see. We found the parameters are set for the proportional controller. And for the next assignment, we will design proportional integral parameters.
Well, if he does, I will tell him. He told me to just do it. I have proportional and control. My eyes are really starting to cross.
Good afternoon. I'm Stuart Wheeler, and fighting examiner back in round 2 after getting beat by the system last week. And had some stuff missing, but hopefully we'll cover everything this time. We're going to go over the background again and a better review of the steady-state operating curve, the step, the sign experiments, and the Bode plots, so we get from those. And we'll talk about proportional only modeling and experiments and its conclusions about this. We have the duct cooling system. We have a fan motor there, blows air through the ducts, and there are heating elements in the ducts that heat up air in there, and the temperature sensors inside the ducts. And we vary the input power percent to this motor, and what we get at our output in degrees Celsius. There are 2 dampers, both of which are closed for our experiments. And we have our steady-state operating curve from our system. If you want to find your output, you just take negative 0.33 and multiply that by whatever input you want to put in your system and add 73 to that, and that will give you what your temperature would be if you change it to that. This is an example of the first order plus dead time model that we did for our system. This one in particular, we find the values of gain, the time constant, and the dead time from these. And here are, we did 3 step-up experiments for these, and 3 step-down. These are the step-up experiments, along with the modeling comparison there. For the dead time, we, mostly for the graphs, it's a little hard to see because it seems almost 0. But on the time constant, it was pretty close together, around between 0.4 and 0.5 minutes. And the gain in degrees Celsius per percent was around for the upper region was negative 0.2, around negative 0.3 for the lower region, and around negative 0.6 for the middle. Here's the results from the step-down experiments we had. For the gain went up to around negative 1 degrees Celsius per percent for each. Varied a little bit from the models. The time constant went up all as well. It's because you're stepping it down, it's turning down the input percentage of the motor, so it's heating up. So it's a little bit slower, and the time constant is around 1.5 minutes for that. This is an example of a frequency response experiment that we did. We find the change in the input percentage and the change in the output as a result of that, and we found the time lag between the input and the output. From this we can get the amplitude ratio and the phase angle. From those we make Bode plots, and from these Bode plots we can find the gain of our system. In this particular case, we found the gain becomes asymptotic at the low frequencies. The gain to be negative 0.47 degrees Celsius per percent. And for the phase angle, you can get the ultimate frequency where the phase angle is negative 180 degrees, and in this case it was 3 hertz. One of our team members also did this alternate method, and I don't really know what this is. It's the relay experiment, but it looks crazy, and the average ultimate controller gain for this one was negative 117 plus or minus 16% per degree Celsius. And I actually think this was done for the middle region, but I think this ultimate controller gain is actually what turns out to be for the upper region, and you'll see what I mean toward the end. And from all of these, for each region, we got the dead time constant gain, and the ultimate controller gain. For the ultimate controller gain for the lower region, that was around 10. For the middle, the alternate method was around 117, and for the upper region it was around 36. After doing, later on I'll show you the controller experiments, and from the proportional only controller experiments, it looks like the middle region, that ultimate controller gain, is actually the closest one to being the ultimate controller gain. And the ultimate frequency for the lower region was around 20 hertz. Around 5 for the middle, and 3 hertz for the upper. This is an example of one of the root locus models we applied at MATLAB. It helps us find the stability of our system, how much, like the damping ratio, how much it's going to overshoot, and the gain at specific points. In these, for each region, we focused on the critical damping, the 1/500th decay, 1/10th decay, quarter decay, and then the ultimate with marginal stability. And the lower and upper regions, it was pretty close. The middle region is a little bit further off, but that's okay. It doesn't mean it's wrong. These are some examples. These are the examples of our modeling the proportional only controller. I like to think of this as, this is how your controller is drunk. Because he's there, but he doesn't really care that he's really far away from where he should be. But he's just there. That's all that matters. He's real sluggish. It's an offset of about 1.5 degrees Celsius. The quarter decay, he's feeling a little bit more lively. He's a little bit closer to where the set point should be, which is the red line. The offset there of about 0.5 degrees Celsius. A little bit closer. He works a lot harder to try and get the output closer to where it should be, but he's still a little bit off. And for the ultimate controller gain, this is your system after about 15 cups of coffee, because he's trying real hard. He tries really hard to get to where we want him to go. He overcompensates for everything. And you'll see that later on in the experiments. Here's some graphs of the lower range for the modeling, and the offset goes down as you increase the controller gain, and which makes sense because it's paying attention more. It's trying to get closer to what you were asking it to do. And the decay ratio goes up because it's trying so hard to get to where you want it to go that it keeps jumping back and forth, that it's overshooting a lot there. And the settling time takes longer because of that too. Again, it's kind of the same story in the middle range. Settling time went up towards at the quarter decay, which kind of makes me wonder if something was missed in the analysis, like you've gone past what it should have been for the controller gain there. In the upper range, the offset again going down as the controller becomes more aware that it's very wrong, and the settling time goes up because of that too, and as long as well as the decay ratio and the overshoot is trying to compensate for what you're asking it to do. Okay, now the fun stuff. This is your system when it's drunk. It's really far off from where you're asking it to be. It's not even close. Like the bottommost line is the output. Like it's like 2 or 3 degrees off. It doesn't even care. There's no overshoot. It's just kind of there. It's just hanging out there. It's not even doing anything. This is with a controller gain of negative 4.3% per degree Celsius. And the quarter decay here for each region there, it overshoots some, but then it fixes itself a little bit. But this, I don't know if this really looks a lot like the quarter decay from the modeling. I'm wondering if we missed something again. Because for our ultimate controller gain, this should have been a lot crazier. And in the bottom right figure, which is the middle region, it does oscillate. It continues to oscillate like crazy. So I'm wondering if for that region, that's the ultimate controller gain. But for the upper region on the top, like negative 32% per degree Celsius, this is not doing it. Like it overshoots some, but barely at all. So it's controlling the temperature really well, but it's not going crazy like it should. So we took it up a little bit further to negative 50% per degree Celsius. And again, like we went in the lower left corner, it's oscillating some there too. But then in the middle region, it's nice and flat. So it's the same story in the top. So it's actually controlling the temperature really well, like it should, which is not what I wanted to see. This is supposed to be the ultimate control gain. I want to see some oscillation. So we made it preposterous. We got negative 130% per degree Celsius, and we finally got sustained oscillation of the output. So that's why I was thinking for the alternate method that had the average controller, ultimate controller gain being negative 117, I'm thinking that might be the most accurate one, because this is how I feel like it should look for really close to the ultimate controller gain. This is what the modeling is showing, and it doesn't know. It's just crazy right now. Yeah, all it knows is 0% and 100%. It gets too hot. Well, let's turn the fan on 100%. Oh, it's too cold now. Well, let's just turn it off. Like, there's no in between. So it just gets crazy, and so it oscillates. There's no in between there for it to instead level out. There's some for the lower region, the experimental results for the overshoot, the decay ratio, and the settling time. Offset was a little hard to tell for most of them because they got pretty close for most of them, which again makes me wonder if we analyzed some of this a little incorrectly. And then the middle region, overshoot, again, the ultimate controller gain, the overshoot should be a lot more than 20%. And so, and again, the decay ratio is at like 0.5. So I'm thinking we might have missed the mark on these. Same thing here, overshoot for the ultimate controller gain was negative 32% per degree Celsius, and it's only overshooting like 20%. That should be a lot higher. So we've covered the background, talked about the stuff we've done on steady state operating curve, step, sign response, the voting plots, and the controller and modeling experiments. And big salmon.
Can you go back to that 6 slide?
6 slides? Which one?